Firstly, I'll just mention that my talk's not going to be statistical at all. I hope that's a comfort and not a disappointment. Mainly, I'm going to be talking about the concept, getting the concept of what we mean by confounding clear into your head, and also knowing what we can do about it and what we can't do about it. Okay, so I'll be talking obviously about definitions. I'll be talking a lot about causes and something called causal graphs, and talking about how we can prevent confounding, and then looking at some of the more fundamental issues, more difficult problems for which we probably would need a second talk and we won't cover here. Okay, well, I believe that confounding is one of the most important issues to hold in your head when you're considering the validity of observational research that is concerned with causes. Now, I work in epidemiology, so the kind of causal questions that we ask are, I've given you some examples here. For example, does hormone replacement therapy, which is often prescribed for women after the menopause, does it have a causal effect on your risk of cardiovascular disease? Does the MMR vaccine, is it a cause of autism? Is shift work a cause of heart disease? So all of these are causal questions, and generally I'm just going to summarise a causal by question in the following slides by saying, is E a cause of D? Now, of course, all my examples are taken from epidemiology, and this is social sciences, but I would encourage you to hold in your head your own pet causal question, so substituting for D, perhaps some favourite outcome that you're interested in, and also encourage you to think that when I say E, meaning an exposure, I don't always mean a kind of external exposure from the environment or a medicine and so on. I might be talking about social deprivation. So I'm using E and D as a shorthand, but I would encourage you to think about these as very, very broad categories. Okay, well, what is confounding? It's something that, it's a label that we might apply to a particular study that is claiming to address a causal relationship between an exposure and disease. And I'm giving you two definitions because I think they're both quite helpful in their way. One of them states that confounding is a lack of comparability. So it's a lack of comparability between the groups that you're comparing. I'm going to, again, as a simplifying feature, just think about exposure as having two categories, exposed and unexposed. So when we talk about lack of comparability, we're saying that those two groups that we're comparing are not really comparable in the sense that even if there had been no exposure, the outcomes would have been different for the two groups. So they're not equivalent groups to begin with. So fundamentally, that is the problem. Now, what is the consequences of that lack of comparability? Well, the consequences is that when you come to measure your association between your exposure and disease, or exposure and whatever outcome you are interested in, that measure of the causal relationship is in fact distorted because of the confounding problem. And we can also go on and say that the fundamental reason why it is distorted is because the exposure that we're looking at is correlated with many other risk factors for the disease. And so what we're picking up is not just the effect of the exposure that we are interested in, but the effect of many other factors as well. So fundamentally, confounding is a bias in our data. How big a distortion or a bias? Well, it can cause a completely false association in our data. So it might be that there is no relationship in truth between E and D, but because of confounding, there appears to be an association in our data. It can hide a true causal association. So here we're saying there might in truth be a true relationship, but confounding is such that when we look in our data, there appears to be no relationship. And in extreme cases, it can even reverse the direction, the apparent direction of the association. So it might be that the exposure prevents disease, but in our data, it looks like the exposure causes disease. So this would really be the very worst type of confounding. Now, I've obviously deliberately painted the worst examples, but to bring to mind that these things can happen, and you should always hold them at the back of your mind. But, maybe in a lot of examples, the effects of confounding are less dramatic. It may mean only that our measure of association, whatever it is slightly biased compared to the truth. So it can be a big or small problem. Okay, well, when should we worry about it? Now, fundamentally, confounding is a causal concept. And if you're not asking a question about causation in your study, then really you don't have to worry about it. So I think the first thing that we have to decide when we're approaching this is, what kind of study am I doing? The examples that I've given you so far were all examples of studies which might address causation. There are many such studies in medical sciences and in epidemiology. Studies where our hypothesis is E is a cause of D, or E is a cause of Y. But not all studies are causal studies. Descriptive studies are studies where we might simply be interested in describing the distribution of disease or of a variable across the UK, for example. So we may simply wish to illustrate variability. We're not asking why is the variability, we're illustrating variability. If you're illustrating variability, you have a descriptive study. When you move on and say, I want to talk about why there's variability, then you're doing a causal study. You may, of course, be trying to do both things in the same study, but you need to keep the two tasks, the two questions separate in your head. And then another study, which I think we need to add there, is a predictive study. Studies where we might want to predict a variable from some other variables. In the medical sciences, for example, we might want to predict people who we think are going to develop disease in the future from a set of baseline characteristics. Again, we're not asking there about cause. We are interested in building the best predictive model. So the first task is to decide, are you in the causal arena or not? Okay, I'm now going to go on and talk to you about an example, which is from epidemiology. But first of all, so that you can understand the overhead, I just want to introduce a measure that we use in epidemiology, which is called the relative risk. So we're assuming that our exposure is a binary exposure, again, keeping things simple. So you're either exposed or not. And a relative risk, if we were talking about risk of disease, is simply the ratio of the risk of the disease in an exposed group divided by the risk of the disease in the unexposed group. For reasons which I won't go into, we tend to favour ratio measures in epidemiology rather than difference measures. And for that reason, when we look at those measures, we have to keep in mind that the no effect value is 1. A relative risk of 1 would imply that the exposed and unexposed there's no difference in their risk. And then a relative risk greater than 1 is telling us that, or suggesting that exposure increases risk, relative risk less than 1, suggesting exposure decreases risk. Okay, so moving on then to my example. And this is taken from a paper which happened to be in the British Medical Journal, which was addressing this question of hormone replacement therapy, HRT, and cardiovascular disease. So the top part of the diagram is showing us, summarizing the results from 6 different studies in terms of their relative risk. So the scale down here is relative risk, and we have the line there at 1. And what we see from the top part of the diagram is that the estimated effect from data that is represented by the squares, all the estimated effects are less than 1. So all the relative risks are less than 1. And this is suggesting that hormone replacement therapy prevents cardiovascular disease. This was really held as a belief for very many years. It was never prescribed for cardiovascular disease. It was prescribed for symptoms. It was also known that it had a good effect in terms of bone density and preventing falls and so on. But then these studies thought, well, let's look at cardiovascular disease, and we found that, lo and behold, all the studies appear to suggest that there was a reduction, and a statistically significant reduction in many studies. So the doctors then could add to their reasons for why you might want to take hormone replacement therapy that it might actually lower your risk of cardiovascular disease. Now, down on the bottom, we have some other studies in which they had adjusted their measures of association for socioeconomic status. So these are doing a different analysis where they're taking account of socioeconomic status in the analysis. And here, of course, we see that most of the effect estimates are now very close to 1. So these studies appear to suggest that there is no effect whatsoever. So our question might be then, is socioeconomic status a confounding factor in the first set of studies? So I'm now introducing the concept of a confounding factor or a confounder. And so I should say that confounders are jointly the factors which are responsible for the distorted measure of an exposure-disease relationship. So we have the question then, well, how do we identify confounding factors? How do we decide what is a confounding factor? And we also have implicit in the picture the idea of an adjusted analysis. So the idea that, okay, we've identified a confounding factor and we can take away the bias that it caused by doing some kind of adjustment via a statistical method. Okay, so then the question is, how do we identify confounders? Now, what I'm going to introduce to you now is really a very, very powerful method for identifying confounders, which doesn't rely at all on any statistical knowledge or any kind of calculation really from data, which, although the examples I will show you are very, very simple, can be extended by complex examples. So that method is essentially causal graphs. And a causal graph is a picture in which we express our beliefs about causes. So I've shown you now on this first picture 3 different pictures. All of them are stating that E is a cause of D. And the reason we're saying E is a cause of D and not vice versa is because of the direction of the arrow. So arrows are very important in this. In the graph before, we see that E causes F and F causes D, but still we have this directed path between E and D. And then at the top graph, I'm simply adding in what is probably the truth, that there are probably multiple causes of D. So the fact that we don't always show them doesn't rule this out. And I will simply use this lower statement as a kind of shorthand for all the others. So it's basically saying there is some causal pathway which links E to D. D might have other causes, but that's not what interests us in our study. Okay. So, in what situations can we see an association between exposure and disease in a study? Well, we will hopefully see an association when E genuinely is a cause of D. We would perhaps see an association when D is a cause of E, although our data wouldn't be able to distinguish between those 2 pictures. But the third one is the one that I'm going to focus on. And in this picture, what I'm showing is that D and E have a common cause, which is C. And whenever we have a picture like this, whether we've got one C or multiple Cs, we will see an association between E and D in our data. So notice that this picture, according to this picture, there is no causal relationship between E and D, but I have not put an arrow from E to D. But we do have arrows from C to D and C to E. And because of this, we will have an association in our data. This is the same diagram. I'm just making a couple of further points here. Well, firstly, we will see an association, and of course it's a false association because there is no relationship between E and D in my hypothetical study here. The second thing I want to say is that we would label C as a confounder in this study. So C is something which we would call a confounder. And then the other important issue is that we can get rid of the confounding if we block this pathway between E and D. We can block that pathway. We can get rid of that association. And we can block that pathway by using an appropriate statistical method. So the conclusion here is that we have, in a simple analysis, we will have confounding by C, but we can remove the confounding by C by an appropriate statistical method. Okay, I want to move on to a slightly more complicated this one you might think about as, we might think about E being alcohol consumption, and D being, well, D might be lung cancer. Let's say lung cancer or some respiratory disease. So let's suppose we're interested in, does alcohol consumption cause the respiratory disease, or is it a cause of respiratory disease? It's a kind of question epidemiologists like to ask so they can tell us all to stop doing things we quite often like to do. Okay, so what else have I shown you? Well, I've also introduced C into the diagram, and C in this diagram is cigarette consumption. And I've also introduced F. F might be a personality trait or some such nebulous concept, which tends to influence our smoking and alcohol consumption behaviour. So a personality trait that tends to make us want to drink and tends to make us want to smoke. So F is a common cause of E and C, and F is a common cause of E and D in this case. So that's what my diagram is claiming. Okay, seems plausible, I hope. So what will happen here? Well, again, the diagram tells us that because we've got this pathway between E and D through these links, we're going to see an association between E and D, even though there is no causal relationship between E and D in this diagram. Now the question is then, how do we get rid of it? Because we haven't measured F. And the theory of causal graphs tells us that if we can control for something in this pathway, we can get rid of the confounding. So, for example, if we were to adjust in our analysis for C, we would break the confounding. So you can think about it perhaps as an analogy of a flow going through these arrows, but if adjustment is like putting a stopcock at one of the variables in the pathway and stopping the flow, breaking the path between E and D, and therefore breaking the confounding. Okay, so there's a lot more to be said about causal graphs, but I want to show you how nice they are in expressing our beliefs and in telling us what will happen if we control for various things that we have measured, and also whether what we adjust for is enough. I might just perhaps point out that real causal associations might be rather more complex than my example so far. This example is courtesy of one of my students who's doing some research on the effect of air pollution on preterm birth. And I encouraged her to think about confounding and to think about causal pathways. And she went off and she came back with this diagram. And maybe this is closer to the true complex nature of causal relationships in humans. Whether we believe all the arrows or not is not the point. My point with this diagram is to say that this is the complexity of human health and behaviour. But my other point is to say that the theory of causal graphs will tell us which of these variables it is necessary to control for in order to remove confounding from our study. And it doesn't mean that we have to control all of them. It may be that we only have to control 5 variables in that network, and we have blocked the effect of everything else. So it's a very, very powerful and I think attractive method for dealing with confounding. And beautifully, you don't have to be a statistician, you just have to be somebody who wants to think causally and who wants to think about the complexity of relationships between variables. Okay, so in practice then, we might come up with a list of variables that we might want to treat as confounders in an analysis. So what conditions might we expect those variables to fulfill before we would treat them as confounders? Well, firstly, a confounder variable must be a cause of the outcome that we're interested in. So C must be a cause of D. Remember, we have to have that linkage between C and D in order for the false association to occur. C must be correlated with E in our study data, otherwise there will be no confounding in our data. But then we have a negatively stated condition, which is that if E causes C, then we should not treat C as a confounder. This is a different diagram from the one that I showed you earlier, where C is a cause of E. If in fact E is a cause of C, then C is not a confounder. In fact, C is a mediator on the pathway between E and D, and we absolutely should not treat C as a confounder, and we absolutely should not try to adjust for it in an analysis which wants to answer the question about whether E is a cause of D. Okay, well, just some further points about defining confounders. The main issue here is that what matters in the end is the joint effect of confounding variables. Now, we haven't talked about so far the direction of a bias that's caused by confounding. But the direction can be in either direction. That we can have confounding which is in either direction. Confounding might exaggerate the apparent association between exposure and disease, or it might underestimate the association between exposure and disease, depending on the correlations in our data. This example I give you here is a study where we're looking at the relation, the effect of an exposure on a health outcome. And if our exposed group were younger than the older group, then we would expect that because age is a risk factor for most diseases, we would expect that that factor alone will produce an underestimate of the effect of exposure. But if we also have, if our exposed group are of higher socioeconomic status than our unexposed group, well then that factor alone would tend to, I meant it to go the other way actually. If they had lower socioeconomic status than the unexposed group, then that factor would tend to mean that our study would overestimate the effect of exposure. But what actually matters in practice is the joint effects. And it is quite possible that confounders will partially, the effects of different confounders will partially cancel out. In principle, they could cancel out to zero. So we then have this slight untidiness, whereby we might say, well, should we really become labeling these things as confounders if their joint effect is zero? And this is slightly slightly untidy in terms of having neat definitions. But I think it's not something that we should waste too much time worrying about. The chances of these biases happening to cancel out to zero is extremely unlikely, and I don't really know of any study where that's been claimed. But of course, it's a theoretical possibility. So I would still put to you that these three criteria that I've spoken of are useful criteria for thinking about whether factors are confounded in your study. Okay, well, moving on. Towards the final third of my talk, we've talked about identifying confounders, and we talked about adjusting for them via statistical methods. Now, there are lots and lots of different statistical methods, and it's not the place for me to talk about those methods, so I really don't want to, but I've put them up here so that you will think of them and follow them through if you need to. We can adjust for confounding via regression models, via stratification approaches, via something called propensity scores, which is very popular in epidemiology at the minute. But of course, we can only adjust for them if we've measured them. A method which is less familiar to me is something called the instrumental variable method, which claims to be able to adjust for unmeasured confounders, but it's not implemented very often because it can be quite difficult to identify a true instrumental variable. So I won't dwell on that. Okay. But for many of us who are planning studies, we think about the confounding problem and getting rid of it, not only through statistical analysis, but also when we're planning the study in the first place. Now, if you remember my definition right at the beginning as confounding being a lack of comparability between the groups that we're comparing, then the question is, well, why don't we try to achieve comparability through the design of our study? And so what do we mean by comparability in this context? Well, we would say that our exposed and unexposed groups are comparable if they would have the same outcome on average if there was no exposure took place. So basically, we're trying to think about, if I took away the exposure, would the progress of these two groups through their life course or through the space in which we're studying them and following up, measuring, would the outcomes on average be the same for the two groups? Well, there are three ways of trying to achieve this via study design. One of them is randomization. So the idea is that we randomize people to exposed and unexposed groups. Of course, there are many, many situations where we can't possibly use randomization. It might be unethical, unacceptable, and so on. It does happen in studies of exposures that we think are actually good for people. So it's something that is used in drug trials because the presumption is that the exposure in this case is actually going to have a positive health outcome rather than a negative outcome. But certainly for many studies in epidemiology, this is not going to happen. The other methods are restriction. We could say, well, let's just do the study looking only at women. Then we can't have confounding by gender because there can't be an imbalance in respect to gender if we do a study simply on one group. And the third group is to do some sort of matching in the design of our study. So we might say, well, for each exposed person, I will try to find an unexposed person who has similar C characteristics. So this requires us at the outset to have some idea of the potential confounding variable C, and we proceed then by trying to assemble the groups we're going to study so that there is this balance on the C variables from the outset. Of course, very difficult to do in practice, and to the extent that we can't do it, of course, we come back to those other methods, which are the statistical methods of dealing with the problem after the event. Okay, I've just got a couple more slides before I finish, which is really to say that my treatment so far has been a little bit simplistic and that there are more complicated issues that you need to think about in practice. Firstly, unmeasured confounders. Just because we don't know about unmeasured confounders, it doesn't mean that they don't exist. And one of the things that we learn a lot in articles teaching us how to draw causal graphs is that we ought to put in things, that even the things that we haven't measured, into our diagram if we think that they are part of the causal chains in the situation that we're studying. So we need to always, in an observational study, realize that there may be unmeasured confounders. If you haven't measured them, you can't adjust for them. If you haven't adjusted for them, you have some confounding left over. Randomization is the only scenario in which we don't have that problem, because randomization tends to balance both measured and unmeasured confounders. Measurement error. To adjust for something supposes that we have measured it precisely. But of course, measurement is itself a complex task. Some of the traits or characteristics that we're trying to measure and control for may be quite complex, and our measurement instruments might be quite simplistic. Now, the truth of the matter is that if you have imprecise measurement of C, where C is the confounder, then you have inadequate adjustment for C, and you will still have some residual confounding. So when people say we adjusted for X, Y, and Z, and say it as though that was the end of the story as regards to confounding by X, Y, and Z, we always need to go back and think about, well, how did they measure X, Y, and Z? And are the measures adequate? Okay. The other thing here is that this whole process of trying to identify confounding variables does require us to make causal assumptions in the first place. And of course, there is no real way of knowing for sure whether X is a cause of Y, ever. Certainly, there is no foolproof test for confounding. Many of us, sometimes when you don't want to think, you just rather do some data analysis, might like to do some tests as a substitute for thinking. But there is no test for confounding. How could there be? Testing and statistical analysis is ultimately the output from those analyses are measures of association. Measures of association are purely statistical measures. They don't carry in themselves any causal implication. So there is no foolproof test for confounding, much as we might like to claim there is one, or some might like to claim there is one. This is important because it is actually possible to create confounding where none existed by controlling for the wrong thing, by adjusting for the wrong thing in your analysis. This would generally happen when you adjust for something that is a consequence, where you've got the arrows of the direction of your arrows in the wrong way in your thinking. And of course, if you have drawn your diagrams and you've thought about the arrows, it's likely that you will get the arrows in the right way. But people who rush into the thing just thinking about it in a very data analytical way aren't thinking in terms of arrows and may wrongly adjust for the wrong thing. One thing is, of course, that is a completely new problem, and that is the problem of time-dependent confounders. So far, I've assumed that we've got our measures of exposure, our measures of social class, our measures of confounders are all fixed in time. In most human observational research, in medicine and I guess also in social sciences, we're more interested in studying people over time. And most of our exposure measures and many of our confounder measures change over time. This creates a layer, several layers of extra complexity when we're thinking about confounding. And in that case, I would suggest that you then go off and read the next stage in this chain of arguments. You read an article about time-dependent confounding and what to do about it, because the simple analyses that I have mentioned so far won't work in this case. And then just finally, some references. I would say that out there in epidemiology, the literature is completely saturated with articles about confounding. Some of them are very, very difficult to read indeed. But I would suggest to you that this writer, Sander Greenland, is a very nice writer and a little bit more transparent than some of the people who write in this field. So perhaps you might look at one of his articles if you want some further reading. Okay, thank you.